Quantum computers explained. The limits of human technology. Since the dawn of time, our brains, fire and pointy sticks defined technology, but today we stand on the verge of something that will change everything. For most of our history, technology revolved around three things: our brains, fire, and pointy sticks. While fire and pointy sticks evolved into power plants and nuclear weapons, the greatest upgrade happened inside our brains. Since the 1960s, the power of our artificial brains has grown exponentially, allowing computers to become smaller while becoming vastly more powerful. But this process is about to hit a physical limit. The components of a computer are now approaching the size of an atom. To understand why this is a problem, we first need to clarify some basic concepts. Fire and pointy sticks evolved into power plants and nuclear bombs, but the greatest leap happened here. Our minds. Since the 1960s, artificial intelligence and computers have grown exponentially. However, this revolution is about to hit a wall, the physical limit of how small we can go. A computer is made of very simple components that perform equally simple tasks, representing, processing, and controlling data. Computer chips contain modules, modules contain logic gates, and logic gates contain transistors. A transistor is the most basic component of a data processor. It's essentially an electrical switch that can block or allow information to pass. This information is made up of bits. A bit can either be a 0 or a 1, and combinations of many bits represent more complex information. Transistors combine to form logic gates. For example, an AND gate produces an output of 1 if all its inputs are 1, otherwise it outputs a 0. These logic gates form significant modules, like those that add numbers. And once you can add, you can multiply. And with multiplication, you can perform almost any calculation. Think of a computer as a group of 7-year-olds solving basic math problems. A large enough group can calculate everything from astrophysics to the algorithms behind a video game. It all starts here. A simple switch called a transistor. Imagine each of these transistors as a child solving basic math problems. Now multiply that by millions. But here's the problem. When we make transistors as small as atoms, classical physics breaks down. This is where quantum physics steps in. But as computer parts get smaller, quantum physics complicates things. Modern transistors are typically 14 nanometers in scale, about 8 times smaller than the diameter of an HIV virus, and 500 times smaller than a red blood cell. When transistors shrink to just a few atoms, electrons can tunnel through blocked barriers due to a phenomenon called quantum tunneling. In this strange quantum world, the rules of classical physics no longer apply. We're hitting a true physical limit for technological progress. Quantum computers don't use normal bits, but qubits, which aren't just zeros and ones. They can be both at the same time thanks to superposition. This changes everything. And this is just the beginning. With each additional qubit, the ability to process information grows exponentially. To overcome this obstacle, scientists are using quantum properties to their advantage and building quantum computers. In a classical computer, bits are the smallest units of information and they can only represent 0 or 1. Quantum computers use qubits, which can exist in both states simultaneously thanks to a phenomenon called superposition. In this state, qubits are a combination of probabilities for 0 and 1, and they collapse into one of these values only when measured. This superposition changes the game. 4 qubits can represent 16 combinations simultaneously, and 20 qubits can handle over 1 million values at once. Another fascinating quantum property is entanglement. This connects qubits in such a way that any change in one instantly affects the other, no matter how far apart they are. Quantum computers configure qubits, manipulate them with quantum gates, and then collapse their states into a final sequence of zeros and ones. This approach allows calculations that would take thousands of years on traditional computers to be performed exponentially faster. From cracking security systems in seconds to revolutionizing medicine by simulating quantum proteins, the applications of this technology are limitless. Is it a specialized tool or humanity's greatest leap forward? We don't know yet, but we're about to find out. While quantum computers won't replace our personal computers, they are vastly superior in certain areas. For example, they can search massive databases much faster and have the potential to break current encryption systems. Moreover, quantum simulations could revolutionize medicine, allowing us to understand proteins and molecules in ways we never could before. We don't know if quantum computers will be just specialized tools or if they will represent a revolution for humanity. But one thing is certain: the limits of technology are still waiting to be discovered, and there's only one way to find out.